Okay, now there's also Kp. So notice I pointed out that C earlier. C stands for concentration. P stands for pressure. Okay, so you can actually calculate a K value based on either pressures or concentration. So if we're using gases, pressures can be really useful, right? So the way that Kp is written then, so we said Kc, it looks like this, right? It's concentration A times, oh shoot, did that backwards, didn't I? It's products over reactants. Silly. C to D over A to B. Pressures are similar, except you're just going to use partial pressures. So it's the partial pressure of C to the C power times the partial pressure of D to the D power over the partial pressure of A to the A power times the partial pressure of B to the B power. So it's just the same. You're just going to use partial pressures, and you can calculate this as well. Now, Kp and Kc are not necessarily exactly the same number. They have a relationship, and this is the equation you will have to be able to use, and that is Kp equals Kc times RT, there's that gas constant, to the delta N power. Now, R in this case, you do have to use the 0.08206 number because Kc is in concentration, it's molarity, so moles per liter. And this has liters and moles in it. So the only way to get this one to work is use the correct R. And then I got to tell you what delta N is. Delta means change in, right, moles. And this is actually the moles of gas. Moles of gas in the products minus the moles of gas in the reactants. Okay, so products minus reactants, like most change in equations are, but it's the number of moles in the balanced reaction. So we're going to do one of these in a little bit, but what that means is how many moles of gas are produced versus how many moles of gas are in the reactant.